Hello everybody, welcome to another video lesson. Today we're going over partial fractions, okay? After today we should be able to write partial fraction decompositions of rational expressions with linear factors and with prime quadratic factors in the denominator, okay? So let's take a look at our concept for today, okay? If I'm given a function or an expression like this, a rational expression, okay, a partial fraction decomposition is when I take this expression and I rewrite it as the sum of two kind of simpler fractions, all right? So we can see here I've got this power of 2 here. Now I'm writing it as the sum of two simpler fractions with the power of 1 in my denominator, okay? Now, each of these that we see here are what we refer to as partial fractions. That's why we're calling this partial fraction decomposition, okay? Because we are looking at this expression as the sum of two partial fractions, okay? So anytime I do this, this is what we refer to as our partial fraction decomposition. This whole right-hand side of my equation here is our partial fraction decomposition when I take this expression, this whole expression, and rewrite it in terms of partial fractions, okay? Or the sum of partial fractions. Okay, so let's go ahead and take a look at some examples on what this process looks like. Okay, if we're asked to find the partial fraction decomposition of a rational expression like 2x plus 5 over x squared minus x minus 2, okay, first thing I need to check is the degree of my numerator and the degree of my denominator. Now, luckily for us, the degree of my numerator is less than the degree of my denominator, okay? So we don't have any extra steps on this one. So from here, we just have to say, okay, what are the factors of my denominator? And I know that I can see that x squared minus x minus 2 factors into x minus 2 times x plus 1, okay? So what we're going to do is start building our partial fractions, okay? So I'm going to rewrite this as the sum, okay, again, I've got this sum here, of one fraction with my x minus 2 as the denominator, and another fraction as my x plus 1 as the denominator, okay? So I'm just taking my factors of my denominator of my original expression and making them the denominators of my partial fractions that we're adding together, okay? And then I have some value a and some value b. Those are going to be my numerators that I need to solve for, okay? So in doing this, now I need to think, okay, what is my LCD? Well, my least common denominator is just the factored version of my original denominator, right? We got x minus 2 times x plus 1. Okay, so if I go ahead and try to start rewriting this as one fraction, then I would need to multiply my first partial fraction by x plus 1 on the top and bottom, and my second partial fraction, I'm going to multiply x minus 2 on the numerator and denominator, okay? So when I do this, now I've got the same denominator, x minus 2 times x plus 1, okay? So since my denominators are the same, the only way for this expression to be true where these two sides are equal to each other is if my numerators are equal to each other, okay? So I can kind of ignore my denominators at this point and just set the numerators equal to each other. And what I did here, I distributed my a and I distributed my b to the x plus 1 and the x minus 2. That's how we have this expression down here. Okay, so from here, I went ahead and I kind of combined my like terms of ax and bx, and then I factored out my x here. So I've got a plus b quantity times x plus a minus 2b. That's what we're left with. Okay, and now from here, I'm going to do something called equating coefficients. Okay, when I equate my coefficients, I need to look at all of my terms that have an x in it on both sides of my equation. Okay, so we can see here my coefficient for my x term is a 2. So that's what I have over here on the left-hand side of this first equation. Now the coefficient for the x on my right-hand side is a plus b, which is how we have a plus b right here. And for my constants here, I've got a constant of 5 on the left-hand side, and this whole term right here represents a constant. So this a minus 2b is what I can put on the right-hand side of this second equation, okay? So now I really have two equations and two unknowns, right? I got an equation 1 and equation 2, okay? And I can work with this like I would a system of equations, okay? So for this one, I'm actually going to build a matrix equation. So I'll have 1, 1, 1, negative 2, 1, 1, 1, negative 2. And then my variables here at this point are a and b is equal to my constants of 2 and 5, okay? So I can go ahead and create an augmented matrix from this. And I've got row 1 and row 2 of my augmented matrix. And I'm going to start trying to get rid of, say, this 1. I'm going to try to make that a 0. So let's go with row 1 minus row 2. And that's going to be the new row 2, okay? So when I do that, I get 0, 3, negative 3. So I'm going to multiply that by 1/3. And I'm going to have a new matrix here. And again, I have a 0 here, which is what I wanted. And I've got 1, negative 1 here. Okay, so now again, trying to get rid of this one, trying to make that a 0. So I'm going to say R1 minus R2. That's going to be my new R1. And when I do that, I get 1, 0, 3. So my augmented matrix looks like this, remembering now that this is my A column, this first column. This is my B column, okay? And then this is going to be my constants column here, okay? So from this, I can see that B is equal to negative 1 and A is equal to 3. Okay, so going back to the partial fraction decomposition that we were doing, okay, we've got our 2x plus 5 over x squared minus x minus 2 is equal to the sum of these two partial fractions, and we just solved for A and for B. So all I have to do now is just plug these in, and our partial fraction decomposition looks like this. 3 over x minus 2 plus negative 1 over x plus 1. And I could have taken this and just made that a negative or a minus, since this is a negative 1. But either are fine, okay? So that's our first example. Let's take a look at another example. Again, we're finding the partial fraction decomposition of our expression here. Now notice I've got the same degree on the top and bottom. So like I mentioned earlier, we're going to have to do a little bit of extra work. But we've done this work before, it's just our long division, okay? So if I do long division here, I see that I get, in my quotient, I've got 3 plus 6x plus 4 over x squared plus 2x, okay? So take a look at this. If you need a little review on long division, maybe go have a look at another lesson, okay? But this would be the long division of this expression up here, all right? So now I'm going to keep in mind that I have this 3 here, and now I'm really going to just do my partial fraction decomposition separately for this remainder, what we have right here, okay? And notice now my degree is 1 in my numerator and my degree is 2 in my denominator, which we want. We want a greater degree in the denominator than in the numerator. So I've got 1 and a 2, so we're good to go. Okay, so now I'm looking at just my 6x plus 4 over x squared plus 2x, okay? And I'm going to break that up after I factor my denominator here. So I've got x and x plus 2. So my first fraction here, my first partial fraction will have a denominator of x plus 2, and my second partial fraction will have a denominator of x, okay? And we know that my LCD is just going to be this factored denominator here of x minus x plus 2, okay? So again, the process, trying to put this into one fraction now, okay, and I've got my a and b that we're trying to solve for. Okay, so it's going to look like multiplying by x for my first partial fraction and multiplying by x plus 2 on the top and bottom of my second partial fraction. Okay, so then I can go ahead and combine those into one fraction on the right-hand side. And now I've got this statement that these two are equal to each other. And since I have the same denominator, my numerators must be the same as well. So I can set my numerators equal to each other as well. And I just went ahead and I distributed my b to my x and my 2 as well. Okay, so I've got 6x plus 4 is equal to ax plus bx plus 2b, all right? Okay, so I can go ahead and factor out or combine my like terms, a and b, and ax and bx, and then factor out that x. Okay, and then I'm gonna go ahead and set up I'm going to equate my coefficients again. Okay, so I've got x. Okay, that's kind of like my first equation. Okay, so I've got a 6 here for my x and a 6 there. Okay, and then the coefficient for this x, I've got a plus b, so a plus b here. That's my first equation. And then for my constants, I've got a positive 4, so I'm going to set positive 4 on that left-hand side. And then 2b is a constant itself, so that's where we get 2b here for my second equation. Okay, so now we can just go through, and since b is easy to solve for, we're just going to solve for b. That's equal to 2. And looking at equation 1, now I can just take this b and plug it right in to equation 1. And when I solve for a, I get that a is equal to 4. Okay, so now again, going back up to my partial fraction decomposition here, this is the expression that I'm looking at, but I also have this plus 3 over here. Okay, so my final answer is going to be that plus 3 plus, now I'm just substituting in 4 for my a and 2 for my b, and this would be my full partial fraction decomposition. Okay, let's take a look at 2 more examples here. Okay, first one, here's the expression that we're given. Now here we're just looking at what happens when we have repeating linear factors. Okay, so when I factor out my denominator here, I actually get x and x minus 1 squared. Okay, so what we have to do here is we have to think of building up this power here that we have for our linear factor. Okay, so what that would look like is a over x plus b over x minus 1 plus c over x minus 1 squared. Okay, so I can't just have, like if I didn't put this in here and I just had c over x minus 1 squared, okay, I have to think about building up to whatever this power is. Okay, so if this was to the third power, I would have to have plus d over x minus 1 cubed, okay, if that was to the third power. Now, why is that? Let's take a look at a little bit of a simpler example. If I had, say, x plus 2 over x cubed plus x squared, okay, that looks like a over x plus b over x squared, again, building to that, okay, plus x plus 1, or c over x plus 1, okay? And that's because this is how we would factor our denominator, okay? Now, if we didn't separate this a, b, and x squared, okay, we would have to write this in terms of a linear numerator, okay? And we'll take a look at another example of that next example. Okay, but since this is power of 2, I would have to write this as a linear numerator with the power of 1, okay? So that would have to be written as ax plus b. Now when I do that, okay, I think I can rewrite this, since this is one denominator here, I can rewrite this as ax over x squared plus b over x squared. And we can see that my x would cancel out with my x squared, and I'm left with ax plus b, a over x plus b over x squared, which is exactly what we have right here when we're building up our powers, okay? Okay, so again, if I have repeating linear factors in my denominator, I'm going to build them up, okay? So I'm going to start off with that factor to the first power, then to the second, third, fourth, however many this power is, I'm going to build term by term up to that, okay? Okay, so now that we've got that new concept, let's go ahead and solve this one. Okay, so I'm going to go ahead and highlight my a, b, and c here. Okay, my LCD again is x times quantity x minus 1 squared. All right, so if I were to go ahead and put this under this same fraction here, okay, it would look something like this. All right, I'd have to multiply my first partial fraction by x minus 1 squared on the top and bottom, and I have to multiply my second partial fraction by x times x minus 1, and I'd have to multiply my third partial fraction by just x on the top and bottom, and when I combine them, I get this fraction right here. Okay, go ahead and foiling this out and then distributing my a. Okay, again, I have to FOIL first and then distribute. Okay, when I do that, I get x plus 2 equals ax squared minus 2ax plus a plus bx squared minus bx plus c. Okay. So we can go ahead and again, I'm going to set up 3 equations now because I have x squared terms, x terms, and constant terms, okay? So again, I'm just equating my coefficients, all right? So for my first one, I don't have any x squared terms over here. So I'm just going to write a 0 right there. I've got 0 x squared terms on the left-hand side of my equation. But on the right-hand side, I have an a and I've got a b, right, that are coefficients for my x squared terms. Okay, since this is x squared, I'm looking at my x squared terms here and here. I'm looking at those coefficients. Okay, so then I'm doing the same thing for my x and for my constant terms. So again, I've got 1x over here, and I've got minus 2a, I've got a minus b and a plus c, okay? And then for my constant terms, I just have a constant a here, and on the right-hand side, and on the left-hand side, I've got a 2, okay? So I've got 2 equals a. So again, 3 equations, 3 unknowns. Okay, so if I go ahead, I know a is already solved for, a is 2, so that's nice. So then I'm going to take a look at 1, okay, my first equation here, and I'll just input a 2 where I have an a. Okay, so when I do that and solve for b, I get b is equal to negative 2. And then I can take a look at equation number 2 here and input, again, a is 2 and b is negative 2, and then solve for c, and I get that c is equal to 3. Okay, so taking a look at my setup for my partial fraction decomposition and just inputting values for a, b, and c, and I get a final partial fraction decomposition that looks like this, okay? 2 over x minus 2 over x minus 1 plus 3 over x minus 1 squared, okay? Okay, last example here. All right, notice here, okay, the difference in this one is that my denominator has a prime quadratic factor, okay? I can't simplify this anymore to a linear factor. Now I've got this prime quadratic factor. Okay, so when I do that, what I actually have to do here is I have to rewrite these with numerators that are linear expressions. Okay, so these have to have a power of 1. Think of them as having a power of 1. So now instead of just a on the top, I need to write ax plus b over x squared plus 1. Okay, and then over here, again, because this is a partial fraction with a prime quadratic factor, I've got to write the numerator as cx plus d. I've got to have a linear expression, okay, with a power of 1 in my numerator, all right? So looking over at my LCD here, that's just going to be the original denominator that we have. Okay, so go ahead and putting this under the same fraction, okay, just taking this, putting it under the same fraction. I've got to multiply my first partial fraction by x squared plus 1 on the top and bottom. Okay, so there should be a parentheses right here, sorry. Okay, and then I'm going to go ahead and, let's see, yep, I'll go ahead and FOIL this out. So I've got ax plus b times x squared plus 1, okay, and I'm just taking away my denominators, just looking at the numerators right now, okay, and then plus cx plus d, okay. So I can go ahead and FOIL out, I get x cubed plus 2x equals ax cubed plus ax plus bx squared plus b plus cx plus d. All right, got a lot going on there, a lot of letters for this math problem. Okay, but we're just going to equate our coefficients again. Okay, this time I've got 4, right? I've got x cubed, x squared, x, and constants. Okay, so when I equate my coefficients, that looks like this. I've got a equals 1, 0 equals b. Okay, that's quite nice. I've got, again, 1x cubed. Okay, and then I only have an a for my x cubed on the right-hand side. Okay, so 1 equals a. And then I have 0 x squared terms on my left side, and I only have a b for x squared on my right side. So that gives me 0 equals b. So really I've already solved for this first partial fraction. Now I just got to figure out c and d. And I can do that, again, by 4 equations, 4 unknowns. So I'm going to look at equation 3, and I'm going to input, where I see an a, I'm going to input a 1, and solve for c, and c is equal to 1. Okay, and then looking at equation 4, okay, wherever I see a b, I'm going to input a 0, and I find that d is equal to 0. Okay, so what that looks like, when I substitute my values in, I'll have 1x plus 0 in the numerator of this partial fraction, and 1x plus 0 in the numerator of my second partial fraction, okay? So we can just simplify that a little bit to be x over x squared plus 1 plus x over x squared plus 1 quantity squared, okay? So a few different variations on our partial fraction decompositions. Okay, good luck guys with your practice.